So now let's consider an example with angular momentum. So this is example 8.4 in the Electrodynamics book by Griffith, 4th edition. So in this example, what we do is we have a solenoid with a radius r, and it has n turns per length, and it has a current I flowing through it. Now there are two cylinders which are basically coaxial with this solenoid. Now let's make these cylinders non-conducting so that the charges don't move around. So the inside cylinder has a radius a, which is less than r. The outside cylinder has a radius b greater than r, and the inside cylinder has a charge q. The outside cylinder has a charge minus q, and the length of the cylinders is L for both of them, and we just want to set the condition that L is much bigger than B. So what does this picture look like? So what we have is we have a solenoid. So we have this solenoid which has n number of turns on it. And then outside the solenoid, I have a cylinder like so. And then on the inside of the solenoid, I have another cylinder like this. And then these cylinders have charge on them. Okay, so then I set a current going through the solenoid like this. So the idea is that the current is going to create a magnetic field, and if it's a modulating current or an oscillating current, it should also induce an EMF. And so if we have a case of a changing current going through the solenoid, we should create both an electric field and a magnetic field. And if I have an electric and magnetic field, there should be some momentum. Not only that, we should maybe get some angular momentum, and then these non-conducting cylinders should rotate, because there should be a conservation of angular momentum. Angular momentum from the fields couples to the cylinders. The cylinders now have to conserve that momentum, and so they rotate. So let's see how we can actually approach this problem. So since the cylinders have a charge on them, the electric field on the cylinders is the charge 2 pi epsilon naught L, because usually it's the charge density, the line charge density, 1 over S. So we've seen this before in different problems. And now this is in the region in between the two cylinders. So basically the electric field created by the cylinder with a radius A. And we found, you can find this using Gauss's law. For the solenoid, the magnetic field is mu 0, n number of turns, the current in the z direction. And so this is inside the region less than. So the outside the solenoid, the space between the solenoid and the bigger cylinder, there's zero magnetic field. But inside the solenoid, there is a magnetic field which has been created along the z direction of it. So, okay, so because of these fields, we can now write down the momentum density, which is epsilon naught E crossed into B, which is equal to mu 0 n I q over 2 pi L S, and that would be S crossed into Z, which turns out to be minus phi. So we have minus mu 0 n I q over 2 pi L S in the phi direction. So now we've got this momentum, which is essentially, if I look at the cylinder, I have a momentum which is now pointing tangential to this circle. The circle, which is now basically the loop encapsulating the inner cylinder. So, okay, so that's in the region of in between the cylinders. So if I take the z component of the angular momentum, so if I calculate the angular momentum, taking some radius r, and I only calculate the z component of that, I would get minus mu 0 n I q over 2 pi L. Whereas, I mean, I said r, but really it should be S. Right there. Okay. So that one, so the interesting thing is that now it's independent of S. It doesn't matter where we are in between those two cylinders. You would get the z component to the angular momentum. If I now multiply by the volume, I would get the total angular momentum. I would get the angular momentum, not the angular momentum density. And so I would essentially multiply this quantity here, minus mu naught n I q over 2 pi L times the volume, which is pi r squared minus a squared times L. So that's the volume of my cylinder. So that's the space in between the small cylinder and the solenoid. So L's cancel, pi's cancel, and what I'm left with is minus, that's in the z direction. So minus mu 0 n I q divided by 2 r squared minus a squared in the z direction. So now I essentially have an angular momentum for the region inside the solenoid. So that solenoid, the inner cylinder should start rotating. Okay, but now let's consider changing the current. So let's say we turn the current off. If we turn the current off, then I should create an electric field, an induced electric field from the changing magnetic flux. And so the electric field that I get is minus 1/2 mu 0 n di dt r squared over s in the phi direction. And this is for a region that's bigger than the solenoid. And if we want to consider the region inside the solenoid, then I would get minus 1/2 mu 0 n di dt s in the phi direction. So that's inside the solenoid. So I have an electric field on the outside of the solenoid, I have an electric field on the inside of the solenoid. If I want to calculate the torque, then the torque would be R crossed into the force, which in this case would be R crossed into minus QE. And okay, so if I put that together, I have the torque on the outer cylinder is going to be equal to Q over 2 mu 0 N di dt R squared over S hat crossed phi. So basically I had to cross, I said R before, but really S is the radial direction. So that's where I get an S here. That's where I get this S right here. Anyway, so if I put that together, what I get is, well, let's work it out for the, so let's clean it up. So I get Q over 2 mu 0 N di dt R squared in the Z direction. And now remember that the torque is the time derivative of the angular momentum. So now if I integrate this torque, I can get the angular momentum for the outer cylinder. Like so. The only thing that's time dependent is that derivative is on the current. So I would get 1/2 mu 0 N Q R squared in the Z direction, and then integrating from some current down to 0. So I'm turning off the current. And I would get minus 1/2 mu 0 N Q R squared I in the Z direction. So that's my angular momentum I would get for the outer. For the inner, I could repeat the exact same procedure by taking that equation for the torque and then integrating with respect to time. What you would find for the inner is I would get 1/2 mu 0 N I Q A squared in the Z direction. So if we look back on this, what we had for the fields, I have here an S, and if I'm calculating the torque as basically R crossed the force, and the force is linearly proportional to E, then it's basically just S times S, I would get S squared. And so in the end, what you would find is you would get this right here for the inner momentum. So taken all together, the angular momentum that you're getting from these electric and magnetic fields is the angular momentum for the outer plus the angular momentum for the inner cylinders. So the fields inside, so if I was to have this situation where I have a solenoid, a cylinder on the inside, a cylinder on the outside, the cylinders have charges to them, but they're non-conducting cylinders, so the charges can't move and create a current. And then I turn off the current through it, so I have a changing magnetic field. That induces EMFs, which then are going to start these things spinning. The interesting thing is that they spin in the opposite directions. The inner is going to spin in a positive direction. The outer is going to spin in the negative direction.